Hello folks, imagine it's the 1950s, a time when medical research was transforming lives. Yet critical questions they remain unanswered at that point in time. There were two scientists named Dr. Edward Kaplan and Dr. Paul Meier who were working independently on the opposite sides of the United States of America, and they were grappled with a common problem: how to measure survival times in patients when some of them they dropped out of studies or their outcomes were unknown. Now, before this breakthrough, researchers they faced a frustrating choice: either to exclude these patients or make risky assumptions, both leading to flawed conclusions. Their innovative minds they converged together to develop what we call the Kaplan Meier method, which is a statistical marvel that changed the face of survival analysis forever. Now, this curve wasn't just about mathematics. It told stories of hope, resilience, and the ticking clock of disease progression. Today, this legacy is more relevant than ever, especially in pediatrics, where every symptom-free day is a triumph. So let's journey together to uncover this powerful tool that shapes decisions that impact children's life. My name is Dr. Saeed Kazmi, and you are watching my YouTube channel. Now, in today's video, we are going to talk about what these two scientists they discovered, the Kaplan Meier Survival Analysis. Now, please don't get freaked out by this word. This is a very common public health statistical tool which is employed in clinical practice to determine the efficacy of various treatment plans. And I will try to simplify this whole concept with examples or some certain research findings from the field of pediatrics that would make you understand this concept in a very simple manner. So let's dive in and get started. So the name is Kaplan Meier Survival Analysis. They also call Kaplan Meier Survival Curve Analysis or Kaplan Meier graphs. As I told you earlier, it is named after these two scientists, Dr. Kaplan and Dr. Meier, who discovered this method. This is a statistical tool, a biostatistical tool, a research tool, which helps us answer certain questions. Now, by definition, because I told you earlier, this is a statistical tool, a statistical method. So this method is used to estimate the what we call as survival probability. Now, this word survival does not mean that somebody is surviving an acute event. Don't take it simply as that this means that somebody who has survived a myocardial infarction or survived a stroke or survived a fatal, like sort of a serious accident. It could be one of those, but when we use the word survival, it also means symptoms-free interval. Like for example, in many pediatric conditions, children might get repeated attacks of the illness. For example, asthma and viral wheeze, which I would be using in this particular lecture. Now, because these kids, they are getting repeated infection, they have to be put on certain treatment, which we do in order so that they have got maximum time symptom free. So for that, various types of treatment are used, various types of medications are used. You might think one is better than the other, but how do we decide if medicine A is better than medicine B in terms of that, let's say A or B has got more symptom free interval when given to these kids? So this time of symptom-free interval, that also means survival. Though obviously this is not survival in literal term that they are not like sort of surviving in terms that they are dying or something, but it simply means that they are surviving the illness, they are surviving the acute attack, or they are surviving the exacerbation. So survival could mean a real survival as well, like somebody who had a very serious incident, let's say a stroke or myocardial infarction or a cancer, and we see how long they survive after being given some medication. But it can also mean some symptom-free interval. So in pediatrics, where mortality is not that high, we mostly, when we are talking about survival, we are looking at symptom-free intervals when giving different types of medication. So coming back to the definition, this is a statistical method which is used to estimate the probability of symptom-free interval over a given period of time. That could be 6 months, 1 year, depending on how long you are going to take that time period into consideration. And that is taken for a given group or population, which in our case would be pediatrics. And again, we can further subdivide it into basis of like age groups, maybe like under 5s, over 5s, depends. So it depends on the researcher. Now it is commonly applied. This method is commonly applied in medical research to analyze time to event data. So for example, we give some medication and we see for how long it has got its efficacy till a child gets the recurrence of the symptoms, the child gets acute exacerbation, or in certain cases death. Okay, that can also be an event, or you can use any other predefined event, okay, which depends on the type of illness that is being considered. So to simplify it, this is a method which actually helps us in detecting, especially when we are comparing two treatments, to see which treatment is better in terms of giving us more symptom-free time period. And again, sometimes remember in general practice, or in, let's say, specific practice like pediatric practice, if you are comparing two medications, sometimes you might see medication A is better. In certain cases, you might see medication B is better. So we have to run certain statistical analysis to see that we are not getting these differences by chance, that there is an actual difference, an actual real difference, which is not attributed just to chance, just like a flip of a coin. So for that reason, it's very important that whenever we see differences, when we say A is better than B or B is better than A, we run a statistical test of significance to see if these differences are just by chance or if there is a real difference. So to see if there is a real difference for these symptom-free intervals between different groups, Kaplan Meier is one of the methods which we can use. Now, moving forward, how do we do this thing? What are the basic steps in doing a Kaplan Meier survival analysis? Number one, obviously, we have to design the study. We have to see what should be the sample size. We make groups. For example, one group of children, let's say, having a drug A, the other group having a drug B, and then we collect the data for every subject. So we give them the medication, we take their baseline data, and then we follow up over a period of time till let's say an event occurs. The event could be an exacerbation of the attack or recurrence of the symptoms, whatever you have decided in your studies. It also takes into consideration those kids or those subjects which are lost to follow up. And this is a very practical thing. When, let's say, you have enrolled, let's say, 100 people in a study and you are following them up, not all of them you would be able to follow up. Some of them would simply, they don't come back to you. Maybe they have gone, they moved out of the area, or they moved to another country, or they are going to another hospital, or they're simply not coming. You don't know what has happened to them. We call them lost to follow up. Lost to follow up. Then there are certain people who might have died during this time. Anything could have happened to them. So over a period of time, we see, once we have taken a group, we see how many of them have got recurrence and how many of them they were lost to follow up. And those people who we cannot account for because they didn't come back to us, because either they moved out or you don't know what happened to them. They might have moved out of the country, moved out of the area, probably going to another hospital. They are known as censored data. Censored data. Censored means that we couldn't get follow-up measurements on them. Even those people who were symptom-free by the end of the study period. For example, you are running the study period for 6 months or 1 year. And let's say there is a fraction of people who didn't get any symptoms at all during this time period. Even when the study finishes, they are asymptomatic. Even that is considered to be censored data. So censored data basically is all those people who you cannot account for, number one, or number two, who have got no symptoms till the end of the study. This is known as censored data. Now, why this is important? In many statistical analysis, people who do not come back to us in the studies, we usually omit their data. We just like throw out their data. We do not take their data into account because we don't know anything about that. But when we are running Kaplan Meier statistical method, we include these people, though despite the fact that we don't know about them. So then the question is, if we don't know about them, what do we do with that data? We make assumptions for that data. Assumption, extrapolation. So whatever data we have got collected, which we have got the records of, we extrapolate that data to these people who didn't come back to us. So that way we account for all these people. We account for all these censored people, or censored data is also included. Then we include it in some of the statistical packages, which could be like R, MATLAB. I personally use SPSS, which many people, researchers, medical researchers use all over the world. Very excellent software. So you can put that data in the SPSS, and the SPSS runs the Kaplan Meier method, because there are so much maths involved in that, so it's not easy to do it by hand. So the SPSS would run. So if you are using SPSS, if you go to the analyze menu and you run the Kaplan Meier Survival Analysis, it would give you a certain table, and it will draw this beautiful graph for you, which is we call as the Kaplan Meier graph, which gives you the information. At the same time, it runs a statistical test to see if there are any differences, whether these differences are by chance or whether these differences are real differences. So we see if there is any statistical difference between the two groups in terms of symptom-free interval or not. So these are the basic steps of running a Kaplan Meier survival analysis. Now, let me explain this with the help of example. I mean, so far the things that I've been talking to you might be passing over the head. You'll be saying, what Dr. Kazmi is talking about? I mean, he sounds gibberish. We don't understand a single word of that. Don't worry, I'm here to make you understand this, okay? So let me take you to the clinical side. As pediatricians, we know globally and regionally pediatric asthma and viral Vs. So multi-trigger Vs or single trigger Vs, whatever you want to call it, it's on the rise. At the moment, like here in UK, we consider that around 18 to 19% of the population, children population, is probably suffering from asthma plus minus viral Vs. And many of these children, they get repeated attacks. So especially in the autumn and winter, they are coming back again and again to the hospitals, or hospitals are overloaded with these Vs. So usually as a first step of prevention, they are either started on some treatment, and usually the first preventive step, if we go according to the stepwise management of asthma or viral Vs, they are either started on montelukast or beclomethasone inhaler. Again, it depends on what dose you are starting them. Usually for younger children, we start them montelukast 4 milligram once every day. Beclomethasone is started 100 microgram per day, or 100 microgram BD for at least 6 to 8 weeks. So these are, the preventers, what we call as preventive management of viral Vs and asthma. So kids are started on these medication. Why we start them on this medication? So that they are symptom free, because if they are coming to hospital every 2-3 weeks, that affects their quality of life. So we have to start them on preventive therapy. Now the debate is, some of them are started on montelukast, some of them are beclomethasone. And if you are a pediatrician, you might have heard this thing, okay, is the child on any preventative? Yes, he was on montelukast, but then they stopped it because it was not working. He was started on beclomethasone, or he was started on beclomethasone, they thought it was not working, they switched over to montelukast. And then you're always scratching your head. Is montelukast better than beclomethasone, or is beclomethasone better than montelukast? Because you hear conflicting stories. Is one medication better than the other in terms of symptom controls over a period of time? How do we know? Because we hear conflicting stories. So why not to do a study to see if one is better than the other or not? A very relevant question. You would agree that either montelukast is better or beclomethasone is better. You don't know, because some say one is better, some say the other is better. Why not to test this thing, okay? Because some, a myth is montelukast is better than beclomethasone, another myth is beclomethasone is better. So let's test this thing. So we design a study and we conduct that study, okay? Now, what is that study? The objective is, we will take 2 groups of asthmatic kids. We treat them in the hospital for acute viral Vs or acute exacerbation of asthma. And once they are being discharged, we say, okay, well, fine. One group, you guys, we are starting you on montelukast 4 milligram per day, okay, and you will have to take it for 6 months. And we take another group in which instead of montelukast, we say, okay, we are starting you on inhaler beclomethasone or Clenil cranial moduli, and you carry on with this thing for the next 6 months. So let's say we have got 25 or 20 children enrolled in one group, 20, 25 or 30 enrolled in another group. So once they've been discharged, one group gets Montelukast, the other groups get what? Inhaled beclomethasone. So let's say we have got two groups, and group 1 in which we are giving Montelukast, let's say over a period of time we have just enrolled 20 kids in that group, and in the beclomethasone we have enrolled 30. So we have got overall 50 children in this whole study. 20 of them, they are getting what? Montelukast every evening. The others, they are getting beclomethasone inhaler twice daily, let's say 100 micrograms BD. And we tell them that whenever the child develops symptoms or acute flare-up, you come back to the hospital and we will see how much time has elapsed between start of this medication and symptom-free interval. And we give this instruction to every child, okay? And we send them home. And we will record their data whenever they come back. And we say, okay, by 6 months, if some of them have got, we will record all the data and we will stop this study by 6 months. So by 6 months, those who did not have any exacerbation or who did not come back to us, we would take that as censored data. But those who are coming back with exacerbation or something, obviously we would record the time between start of the treatment and the start of the symptoms. Okay, as simple as that. So this is the study, let's say a hypothetical study or a real study that we have designed, and we are doing that. Okay, and let's say we have completed the study. So by the end of the study, we found out that group 1, in which we had 20 children who had Montelukast every day, we found out that 17 of them, they came back after some time. Okay, we've got the data, like somebody had like symptom-free interval of like 30 days, some had 40 days, some had 90 days, while 3 were symptom-free by the end of the day. They didn't come back, okay, because they were symptoms-free. They did not had any acute exacerbation, so that's why they didn't come. So we call that censored data. In group 2, in which we had given them beclomethasone, 25, they came back over a period of time because of acute exacerbation, and we had their intervals, like, you know, different times intervals recorded, while 5, by the end of the study, they did not come back to us. Why? Because they did not develop a symptom, or maybe they went somewhere, okay? But we will consider them as censored data. I told you censored data is either symptom-free by the end of the study, or they didn't come at all, lost to follow. Okay, so we have got this. So we have got the record of 17 people in group A and 25 in group in B. Okay, so now we put this data in SPSS. Okay, so we like put this data on Excel sheet or whatever what you call software you're using. Now I've given you a screenshot of this data being entered into SPSS. So where you can see the ID is again the chronological number of the patients. Group 1 or 2. 1 is those who had Montelukast, and group 2 is those who had beclomethasone. And the symptom-free interval are the number of days where they were free. So for example, in group number 1, the patient number 4, he came back after 150 days. So like he was, let's say 150 days would be 5 months. So he was symptom-free for 5 months, and the study was for 6 months. So at 5 months, he came back because he had acute exacerbation. The patient number 5 was group 1, and he came back after 30 days. So he just has symptom control for 30, and he came back in a month's time. So again, different types of data for different people. Okay, and the fourth column you can see is for censored. So censored means if they came back to us, okay, they were not censored because they came back and we had their data recorded. If they didn't come back to us, then 2 number is given for censored. Censoring means like they were symptom free or they didn't come back to us, they'll go lost to follow. Let's say, so we have put all these record in the SPSS, we have entered this data, and now we run an analysis, and this is what we get. So you see a step ladder going downwards, a ladder type of a graph which is known as Kaplan Meier survival curve. So Kaplan Meier curve is a graph, as simple, it's a graph. So the graph, you know, always has got 2 axes, a y-axis and a x-axis. In y-axis, we always get the probability of symptom-free interval. So for example, when you started somebody, okay, when you started, he hasn't got any symptom. Let's say 20 kids were started on Montelukast. When they were started on Montelukast, what happened? At that time, there was no recurrence because they just recovered from the acute attack. So the probability of symptom free is 100%. As soon as somebody gets it, then the probability decreases by, for example, in 20s, the first one gets the recurrence, he comes back to the hospital, it's recorded. So this one is out of the study. Now, how many left? 19. So the probability would of recurrence, okay, usually as like somebody gets attacked, it would go down, it would decrease with the passage of time. So on the y-axis, you have got the symptom-free probability, which is always 100% to begin. And 100% is written as 1.0 in statistical term because we have to take probability between 0 and 1. In other words, between 0 and 100%. So we write it simply between 0 and 1. So on y-axis, you've got the probability. Always some people call it survival probability. In this particular call, because it's not survival, it's not about, we are not recording death or anything, it's symptom-free interval. So we, for the sake of simplicity, we call it symptoms-free interval probability. So this would be on the y-axis. Axis is always about time, and time here is how much? 6 months, which is 180 days. Okay. So over a period of time, what happens? If you see, let me explain this. So on the left side of the graph, you see it always starts with 100% probability 1. So this blue line is for Montelukast group, and the red line is for what? Beclomethasone group. So if you see somewhere around 30 days, maybe, or 20 days, okay, every time you see a dip down. So see, this step ladder has got two parts. One is the horizontal line and one is the vertical line. Every time a vertical lines happen, it means an event is recorded. So let's say at around, let's say this would be somewhere 20 days. The first patient in the Montelukast group, he had an exacerbation. So we would record it as a vertical line. Okay. Then at around 30 days, another patient in Montelukast group had an exacerbation. He came back. So we put another line here. Okay. So on which day he came, we will just put a line here. And the same goes, like somewhere around 25 days, the first beclomethasone child returned back. Then somewhere around like 30-35 days, the second one came around. So you can see every time there is a step down, a child is coming back with exacerbation. So you see, if you have a general outlook, in the beginning, you see that the Montelukast group kids are returning earlier as compared to the beclomethasone. But then somewhere down the line, you see that the beclomethasone kids, they are coming back with exacerbation, and Montelukast is taking more time. And then as you go down, they become more and more close to one another. So in the beginning, it seems like Montelukast is slightly working better, beclomethasone is slightly working better than Montelukast. Then somewhere around here, as the days passes between 2 and 3 months, we see that Montelukast is working better than the beclomethasone, and then somewhere down the line they are almost equal. So one thing that is usually used in when we are interpreting the Kaplan Meier curves is the median survival or the median symptom-free interval. Median is a word which is used for 50% of the population, or in other words, 50% probability. So we see where the 50% line falls. So here is the 0.6 of 0.5, or the 50% probability is here. So if I draw a line from the 50%, I would see that the 50% or the median symptom-free interval for beclomethasone is around, let's say, 60 days. And for Montelukast, it is 70 days. In other words, 50% of those who are given beclomethasone, they have got no symptoms till 2 months. While those who are given Montelukast, they have got slightly more symptom-free time interval as compared to what? Beclomethasone. So apparently seems like probably at median level, beclomethasone is slightly inferior to Montelukast. Montelukast is slightly working better. But if we go down, then we see they are quite close to one another. Rather, at the very end of the study, beclomethasone is slightly better, because you see the graph is slightly higher, because the probability of symptom free is slightly better in beclomethasone as compared to montelukast. But also don't forget that these lines are very close to one another. So apparently it seems like at certain point montelukast is working better, at certain point beclomethasone is working better. But if we run a statistical analysis on this, and remember, when we've got the Kaplan Meier survival curve, the best statistical method is a log rank test. A log rank test. Remember, we don't do a t-test or an ANOVA, we do a log rank test. Whenever you hear about Kaplan Meier survival curve, remember log rank test. There is another method which is also known as Koch regression hazards model. Forget about that, I will explain it in some other lecture. But when you say Kaplan Meier survival curve, 95% of the time we run what we call as log rank test. So when we run the log rank test on this one, look, what does it show? The significance is 0.966. Now, if there was a real difference between these two medications, then the significance should be less than 0.05. It should be less than what? 0.05. Here it is 0.9, which is far more than 0.05. It's quite more than 0.05. So this difference, whatever you see at some point, montelukast being better than beclomethasone, in other areas beclomethasone being better than montelukast, this is all because of chance. This is all because of chance. It might be because of their underlying ages, like certain confounding factor, or maybe something explained by genetics or by race or by nutritional factors, whatever. There could be so many sort of confounders over here. But what it shows, that the differences that you are seeing here, that montelukast being better than beclomethasone in one area, in let's say at some point, and then beclomethasone being better than montelukast at some other point in time, it was just pure chance. There is no difference. Next time you do the study, you might see something else. So there is no real difference between montelukast and beclomethasone. So this log rank test with a significance level of greater than 0.05 is telling us that there is no statistically significant difference in symptom-free interval between montelukast and beclomethasone. Whatever differences you are seeing are individual differences, and it doesn't mean that there's the next time you do the study, you will entirely get a different type of results. So it's telling us beclomethasone, montelukast are not better than one another. As simple as that. Yes, it does not mean there might be some other clinical significance over there. For example, montelukast is easier to administer. Montelukast comes in the form of sachet, so it's easy for the parents to mix it in something and give to the children. While beclomethasone is an inhaler, so you know some of the kids, they don't like these masks and spaces being put on their face, so they might fight off these things. So it might not be easy for the parents to give it to them. That might be one of the reasons that they say, oh, beclomethasone inhaler is not working, because the technique is not proper. So there might be clinical significance of these things, but no statistical significance. So montelukast and beclomethasone are not better than one another. How? Because we have run a study, and this study and the statistical method is telling us that there is no real difference between these two groups. So this is the beauty of the Kaplan Meier survival curve and the statistical test associated with that, which we call as log rank test, which tells us if there is a real difference between two treatments or not. See, so we applied this concept on children who were getting repeated asthma, and we start them on montelukast and beclomethasone, and some parents were saying this is better than the other. So we can tell them, oh, there is no real difference between these two things. They are the same thing. It's just by chance. You are, in your case, it is working better than the other. Maybe next time, so the beclomethasone works better than that. So there is no real difference between the two groups. And how do we know? By running the Kaplan Meier survival analysis. So to summarize it, it's a statistical test for studies in which efficacy of a medication is determined over time. So not only in asthma, in any other chronic condition, if you want to compare two groups or more than two groups as well, like for example, you can have one group of beclomethasone, one group of montelukast, and third is placebo, where nothing is given, and you can compare three groups as well. So Kaplan Meier Survival Analysis, it's a statistical test, and it's a very good test for studies in which the efficacy of a medication or an intervention is determined over time. It is better than using t-test. Some people would say, okay, if you are, why can't you simply take the times between the two groups, let's say, and because time is a continuous interval, you can take the average of both the times and see if there is any difference, and you can run the significance by a t-test, or if more than two groups, ANOVA. But remember, if you are running the t-test for comparison of means between two groups, or ANOVA if there are more than two groups, those tests, they do not take into account the data which is missing, because if there is missing data, 5 people in one group, 3 other, you will have to throw that data out if you are running this test. And if you throw that data out, then you don't know, because that would cause skewed results. Skewed result mean that you have introduced something which is distorting the actual results. So you can get skewed results, you can get biased results. So that's why t-test or ANOVA is not used in these methods. When you are determining the efficacy of intervention medication over time, you cannot use them. You always run a Kaplan Meier survival analysis with log rank test of significance. So Kaplan Meier statistical test is a very beautiful statistical test for determining the efficacy of medication or intervention over time. I hope with this example of pediatrics, now you understand what is a Kaplan Meier survival analysis curve, why it is used, how it is done, and what is the beauty of this test. So if you've understood that, please subscribe to the channel. Have a very good day. Take care and bye-bye.